studying for, you know, I know a lot of the people who take this class are in biology and chemistry and have done a lot more of that kind of stuff. Thanks, come back. And it's just a lot different studying for this. Like note cards don't help you. It doesn't help you. It does help, but it's not enough to just read and reread your notes and memorize stuff. You just have to put the solutions away, put the notes away, and work on problems. That's where you learn this stuff, you know. And so anyways, if you feel like you studied the wrong way and want some tips, please come talk to me. Okay, so exam 1. The first question was a unit conversion thing. So we started with -80 miles per hour squared, and I'm going to write hour squared as hours times hours. And we're trying to convert to millimeters per minute squared. So to convert the mile to meters, so, okay, first we're gonna go miles to meters, and then we're gonna go meters to millimeters. And the most common problem that I saw on this was in the step going from meters to millimeters. So 1 mile is 1609.344 meters. 1 hour is 60 minutes. Then there's, you know, we've canceled one of those hours. We need to do it again. And now we're at units of meters per minute squared. So now the last thing we have to do is go from meters to millimeters. And so if you're going from something with no prefix to something with a prefix, the approach is always the same. First, write down the thing with the prefix. Okay, 1 millimeter. And then replace the prefix, so set that equal to, replace the prefix with the definition. So 1 millimeter is equal to 1 times 10 to the -3 meters, okay? And now this is your conversion that you're gonna use. So we wanna convert, so meters are in the numerator, so we want the 1 times 10 to the -3 meters in the denominator, the millimeters up here. And if you multiply this out, you get -3.58 times 10 to the 4th millimeters per minute squared. A ton of people did this well, a ton, I don't know, 5 to 10 people did this backwards. Said 1 meter is equal to 10 to the -3 millimeters. With that kind of stuff, it also just always helps to just think, does it make sense, you know? So something times 10 to the -3 is smaller than 1, you know? So does it make sense that if you take a meter stick, you can fit less than 1 millimeter in there, you know? And if you think about it that way, you can catch that kind of mistake a lot of times. Okay. Anybody have any questions about that one? Then the second question is one of those where a motion is described and you have to sketch out a position versus time graph. So this object is rolling on an incline. These two are 1 meter apart. These two are 3 meters apart. This is called the point B. This is A, and this is C. And the motion starts at A, goes to B in 2 seconds, From B, it rolls back down to A in 2 more seconds. And then it rolls to C in half a second. Well, before we even start thinking about the positions of these points, you can fill out what the stopwatch says at each of these instants. So this tells us that time is equal to 0 at A. So the stopwatch says 0 there. That's when you turn it on. And then you just keep adding up the times. So this is 2 seconds. This is 4 seconds. This is 4.5 seconds. And now let's think about the positions. It says that the 0 position is at C. And the positive is this way, which means the other way is negative. And now to think about the positions of these points, remember that the position combines 2 things. How far you are from 0, and then a positive or a negative telling you which direction from 0 you are. So at A, you're 1 meter from 0 in the negative direction, and so that is -1 meter. And then at B, you're 4 meters from 0 in the negative direction, so this is -4 meters. Any questions about labeling those? And now that you have these labeled, you can see that at this first point, you're at -1, -4, back to -1, back to 0. Yeah.
Because it's -1 plus 3, how is it 4?
Yeah. Well, we're just trying to figure out a distance from, so think of the distance from 0 first and then put the plus or minus on it. So if you have to go from 0 to get to B, you have to go 1 meter and then 3 more meters. So you're 4 meters away. Do you see that? Like how far would you have to walk to get from the 0 to here? You'd have to walk 1 meter to get to this spot, then you'd rest, and then go another 3 meters. So you've gone a total distance of 4 meters away from 0. And then it's in the negative direction, so you put the negative on the 4. Okay, so now I always fill out a little table with time and position. So at that first instant, the time is 0, the position is -1 meter. The second instant, the time is 2 seconds. The position is -4 meters. At the third instant, you're at 4 seconds. The position is -1 meter. And then finally, you're at 4.5 seconds. And the position is 0. And now one by one, you're just plotting these points. Plot the point 0, -1, the point 2, -4, and just keep going down for all 4 of those points. So this would look like this. If this is position and this is time, there's -1, -2, -3, -4. And the times, there's 1 second, 2 seconds, 3 seconds, 4 seconds, 4.5 seconds. So plot the point 0, -1. Plot the point 2, -4. The point 4, -1. And the point 4.50. And then fill that out. Any other questions about that? And then there is a 1D kinematics problem. So this object is launched straight up into the air. And then comes straight back down. Its starting height is 2 meters. And its starting speed is 20 meters per second, and it starts out moving up. And we want to figure out the height at the highest point. And the velocity at the instant just before it hits the ground. The first thing we have to do is choose a time equals 0 and a time final instant. And one thing about this problem is the time final is going to have to change between part A and part B. So I'm going to write this as part A. So time equals 0, I'm going to do when it's launched. And for part A, if you're trying to figure out something at the highest point, you need your time final to be at the highest point. Otherwise, you can't do this problem. And then we have to choose a 0 position and a positive direction. I'll choose them like that. And now we'll go through what we know and what we want. We don't know time final. We don't know how long it takes to get to the top. We know the acceleration is negative 9.81. P initial is 2 meters. P final is what we're trying to find. V initial, we know the speed is 20 meters per second. It's up, which we chose as the positive direction, so we want the positive there. And then the thing that you're always going to use if you're calculating something at the highest point is that the velocity at that point, in this case it's v final, is equal to 0. And the equation that works here is 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So negative 19.62 times the quantity pf minus 2 is equal to 0 squared minus 20 squared. One mistake I saw a few times was that people treated the negative in this equation as if it's squared inside the square. And so then that negative becomes a positive, but that messes up the answer. That negative has to stay outside here. This is, like, you can think of this as this. You're only squaring the stuff in parentheses, okay? Okay, so negative 19.62 times the quantity pf minus 2 is equal to negative 400. And you get an answer, okay. Another thing that I saw a few times is people didn't treat it like this negative 19.62 has to be distributed through these. So people would multiply the PF times negative 19.62, but not the negative 2. You can't do that, okay? Because these are in parentheses. You can just right here divide both sides by negative 19.62, and then you get PF minus 2 is equal to 20.39. And now add 2 to both sides, and you get PF is equal to 22.39 meters. Any questions about the first part? And then the second part, You can keep the same time equals 0 instant, but you need to choose a new time final instant or you can't do this problem. So time equals 0, keep that the same, but time final now is going to be the instant right before it hits the ground. A couple of people changed the time equals 0 instant to be the highest point now that you know that position and you know the velocity. And you can do that, but I think it's simpler to just keep the same thing whenever you can. Then anything you know at that instant that you knew before, you still know. So like PI will still be the same, VI will still be the same. Okay, so we don't know TF. We still know acceleration is negative 9.81. PI is the same as it was before, 2. PF this time we know is 0 because it's when it hits the ground, and I put my 0 position on the ground. VI is still positive 20, and we're trying to find VF. And you can use the same equation again, 2A times the quantity PF minus PI is equal to VF squared minus VI squared. So negative 19.62 times the quantity 0 minus 2 is equal to VF squared minus 20 squared. And so we have negative 19.62 times negative 2 is equal to VF squared minus 400. Multiply these together and you get a positive 39.24. Add 400 to both sides, and I'm going to switch sides of these things, but we get VF squared is equal to positive 439.24. Take the square root of both sides, and here's your last chance to make a mistake. If you take the square root of a variable, you have to consider that it can be positive or negative. So VF is equal to plus or minus, square root of that is 20.96. And now in math, you're done because there's nothing else you can do. But in physics, we're talking about a specific instant, and so you have to think about what's happening physically. This thing is moving down, and so the velocity is negative. Any questions about that? I talked to a couple people who said that this problem, they started doing 2D and then had to switch to 1D. I want to show you something about 2D and 1D. Like if you're using 2D kinematics to solve a 1D problem, you always can do it. It's not the simplest way. And you'll just see, if you think about everything right, that it reduces to the 1D stuff. So let me say, let's do A again. You know, part A again, if you do it as 2D. Okay, well this time, we still have this distance of 2 meters. This thing's still just going straight up into the air and straight back down. I'm going to put my coordinate system where I pretty much always do. The origin's on the ground, right underneath where the object is at time equals 0. Time equals 0 is still going to be at the instant that it's launched. Time final is still going to be at the highest point. We don't know time final. We know that the acceleration, now we're doing it as 2D, so this is 0, negative 9.81. P initial is 0 for x, 2 for y. P final, well, we know that, well, let's say we don't know anything about that and we're trying to find P final y. Okay. V initial, okay, so now you have to think about a velocity vector. It's going straight up, so if you have so this is the initial velocity vector. It has a magnitude of 20. If you think of putting the tail of that vector at the origin, you're just trying to figure out what the coordinates are of that point. So what are the components of that vector? 0 for x, 20 for y, okay? You also could think that that's a 90-degree angle and use 20 times cosine and sine of 90, but I do think you should get in the habit whenever something's on a positive axis or a negative axis, you should just be able to eyeball that. This is in the direction of the positive y-axis, so it's just going to be 20 in the positive y direction. Okay? So VI is 0.20. And it's the highest point, so VFY is equal to 0. And now you have 6 possible equations, but the one that works is this, 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. And this reduces to exactly what we got before. So you got negative 19.62 times the quantity PFY minus 2 is equal to 0 squared minus 20 squared. And you can see you're just solving for this exactly the same as you did in the 1D case. So you can always use a 2D approach and it'll reduce to a 1D problem if it's a 1D motion. And then the last one is just the vector stuff. Number 4. So the vector that it gives you is like this, where this angle is 20 degrees. And you need to represent it in 2 coordinate systems. The usual one, and then one with the positive x-axis up and the positive y-axis to the left. Okay, so for part A, here's the coordinate system. Don't rotate the vector, just put its tail right at the origin. This angle is 20 degrees. So the angle theta from the positive x-axis to the vector It would be 180 to go all the way around to the green negative x-axis. But we're 20 degrees short of that, so it's 180 minus 20. So theta is equal to 160. And so you have 15 times the cosine of 160, 15 times the sine of 160. And that gives you negative 14.10, positive 5.13. And the second one, I mean, when people make mistakes on this, it's almost always the same thing. You think, okay, now I'm rotating the coordinate system, I rotate the vector, and then at that point you're so confused, like, how do I, now I get the same angle and like but remember that rotating the coordinate system is what you're doing. That vector doesn't change. So the coordinate system is like this. Just imagine picking that vector up and putting its tail at the origin. This angle is 20 degrees. And so the angle you want goes from the positive x-axis to the vector. If you went all the way to the y-axis, that would be 90 degrees. This is 20 degrees short, so the angle is 70. And so the vector is 15 times the cosine of 70, 15 times the sine of 70. And you get positive 5.13, positive 14.10. Any questions about that? Okay. Does anyone have any homework questions you'd like me to go over? Anwar?
Sorry.
Okay, so last time I talked about the rules for free body diagrams, right? And these FBDs, these free body diagrams are important. You have to use free body diagrams every time you use Newton's second law in this class, okay? It shows you what all the forces are, everything that goes on the left side of Newton's second law, and then all you have to worry about is the stuff on the right side, the acceleration and the mass. And one of the things I said for free body diagrams is, okay, so you draw the downward force vector that gravity applies, and then it says, look for all the points where the surroundings make contact with the boundary. Okay, that part, no problem there. And then it says, draw an arrow in the direction, at each one of those contact points, draw an arrow in the direction of that force, okay? And that's where, like, I need to tell you some stuff, because, like, what's the direction of all these contact forces? So that's what we're gonna be starting today. And I think the last thing I said at the end of class last time was, here are the types of forces that you're gonna see. First, there's gonna be a weight force. And the only other type of force that you're gonna see are contact forces. And we're going to break contact forces up into 3 different types. The first one is pushing forces. The second one is pulling forces. And pulling forces we're always going to think of as being applied by a cable. Even if there's no cable there, we're going to imagine that contact being replaced by a cable. And then the third one is friction. And so for the next 2 days, we're just going to one by one go through these force types and talk about how to know the direction of each of these force types. Okay? Okay, so the first one is pushing forces. So what is a pushing force? A pushing force is one where the surroundings prevent the chosen object from invading its space. Okay, so if I run at the wall, I can't go through it, right? And what the wall does to keep me from going through its boundary is apply a force. Okay, that's a pushing force. To identify a pushing force, you can imagine wrapping your chosen object in like a puffy coat, you know? And the question is, does that coat get pushed towards the body, you know? Does it get compressed towards the body of the object, or does it get pulled away? Okay? I don't think I've ever said that before, but I'm still writing it in the notes. Okay, so if the object is in a puffy coat, the down gets compressed. The difference when we get to pulling force, you don't have to write this down, but the difference is like a pulling force would be like not me trying to run through the wall. It would be me trying to run away from the wall, and it's keeping me from getting away. Okay. So as an example of a pushing force, let's say we have 2 carts rolling along a horizontal surface. So a 1 kilogram one, and then a 2 kilogram one. And let's say there's a 50 Newton force applied this way and 100 Newton force applied this way. Okay, so if you think about the 1 kilogram cart and imagine it wrapped in a puffy coat, where are the 2 places where the down in the puffy coat gets compressed? One is at the wheels. If the ground wasn't pushing up on the wheels, that cart would sink into the ground. And the other one is here. And for the 2 kilogram cart, again, the ground is pushing on the wheels. And here, the puffy coat would get compressed by the 1 kilogram cart. Okay, so what's the direction of the push force? So the pushing force direction is always perpendicular to the surface of contact. And toward the chosen body. That force vector acting toward the chosen body is the thing that compresses the coat. Okay? So free body diagrams of these. So here's the 1 kilogram cart. A free body diagram has a weight force down that's equal to 1 times 9.81. So 9.81 newtons. This 50 Newton force is acting on the 1 kilogram cart's boundary. The 100, notice, is not acting on the boundary of the 1 kilogram, so we don't put that in there, okay? So we'll have the 50, but not the 100. And now the two pushing forces. The surface of contact is the ground, so we know that perpendicular to it is up or down. And now we have to choose whether it's up or down. It's toward the chosen body. So I'll do it like that. And I'll give it a variable name. The one I'm going to give it is capital N. We'll use that a lot. And how do you know when I'm using a variable capital N versus the N for newtons? That can be confusing to people. I'm always going to put the fancy shoes and hat on the variable. So if it's newtons, it's just going to look like this. Okay? Plain, ugly even. And here, it's ready for the ball. Okay? Okay? And then there's one more pushing contact. The surface of contact is this. So perpendicular to it is either to the left or the right. And then it's toward the chosen body, so that way. And I'll give this a variable name. I'll call it R. Any questions about that one? And now we'll go to a free body diagram of the 2 kilogram cart. So here's the outline. There's a weight force down that's equal to 2 times 9.81, so 19.62 newtons. The 100 Newton force acts on the boundary of this one, but not the 50. Because if you just look at the boundaries, they're just not on it. You know, you're only putting the stuff, you're putting the weight, and then you're putting the stuff that happens to the boundary of that body. Okay? Then there's a pushing force up from the ground. It's not necessarily the same one as this one. In this case, it's not going to be the same. So I'm going to call that N again, but I'm going to give it a subscript to make it a different variable. And then there's the pushing contact toward the body that's applied by the 1 kilogram. And I'm going to give this a variable name, but I'm going to do something that is going to blow your minds. I'm going to give this the same variable name as this one. Okay? And I'll explain why that is. Anybody have any questions about that? Where those directions came from? Okay, so two things that I want you to remember. Notice. The first one is what I said about the variable names. Don't get the variable for what's called the normal force. That's fancy N, confused with the Newton symbol. N. The variable let's say will always be fancy, and the Newton's N will always be plain. Okay? Then the second thing is if bodies A and B push on each other, let's say the pushing force has the same magnitude on each body, and that means that you'll use the same variable. So use the same variable on each. Okay, so let's look at these free body diagrams. That's the R's that I did here. Notice that force comes from these two things pushing on each other. So when I do the free body diagram of 1 and I do the free body diagram of 2, I use the same variable for those pushing forces. Okay? It doesn't happen anywhere else in this example because this is the ground pushing on 1. This isn't 1 pushing on the ground. Okay? And so it's not the same object pushing on each other. You know what I mean? Anybody have any questions to clarify that? This is actually our first glimpse at an important law of Newton's. Anybody remember what that is from high school physics or anything like that? This is our first glimpse at Newton's third law. And you've probably heard the phrase or a paraphrase of Newton's third law. In his book, when he wrote it, it was worded something like, for every action, there's an equal and opposite reaction. That's kind of hard to make sense out of mathematically, but this is what it means mathematically. If two bodies are pushing on each other, and you go from analyzing one of them to analyzing the other one, use the same variable. Okay. Anybody have any questions about that? Yeah.
On your drawing,
Mhm.
why is the downforce on 2K and not regular gravity?
Yeah, because you multiply the mass times the acceleration of gravity. Yeah, because, so you know that gravity pulls harder on heavier things than on lighter things. Like, for example, if you put a stapler on that table, it sits there. If you put an elephant on that table, it smashes the table. That's because gravity's pulling a lot harder on an elephant than it is on a stapler. Okay. Any other questions? Let's do another example. Why not? My computer forgets where my pen is every once in a while. Okay, so let's say we have a 2 kilogram cart in contact with a 4 kilogram cart. In contact with an 8 kilogram cart. And there's a force applied this way of 80 newtons with the plane N for newtons. And we're going to draw free body diagrams of each of these. So free body diagram for the 2. There's a downward force of 2 times 9.81. That's the weight. There's a pushing force up from the ground. I'll call that N2. And then there's a pushing force from the 4 kilogram. I'll call that RA, let's say. The 8 kilogram cart isn't touching the boundary, so that doesn't go there. And the 80 Newton force doesn't contact the boundary, so that doesn't go there. So this is it. That's done. Now, free body diagram of the 4 kilogram. There's a weight force down that's equal to 4 times 9.81, so 39.24. There's a pushing force up from the ground, and I'll call that N4. Oh, I said normal force, but I didn't say what normal force means. When I'm using these fancy n's as a variable, that always stands for normal force. Normal means perpendicular, and so that's what that n is for. And it's just, you can use any variable. You could use x or q or s or whatever, but this is a common variable name people use, so it's a, you know, to communicate with other people doing physics, this is a good name for it. And then R stands for reaction. So that often is a label that people give when two objects are in contact. Okay, so now we have to think about the horizontal forces. Is the 80 Newton force acting on the 4 kilogram cart? No. The 2 kilogram is pushing on it. So over here, there's a force. Do we know the name that we have to use for that variable, or is it a new variable? Yep, that has to be RA, perfect. And then the 8 kilogram is pushing. Do we know the name of that one? That's not RA because so RA is what happens when 2 and 4 push on each other. It doesn't have anything to do with 8, okay? So I have to give that a new name. I'll call it RB. Ooh, Arby's. I'm thinking Arby's. Remember that commercial? And now the free body diagram of the 8. There's a weight force down. 8 times 9.81 is 78.48. There's a normal force from the ground, pushing force from the ground that I'll call N8. Does the 80 Newton force act on this one? Yes, so the 80 goes over here. And now there's a pushing force that's applied by the 4. Do we know the name of this? This is RB. And you're done. This gives you every bit of information that goes in on the left side of Newton's second law for each one of these bodies. So with this, we can fill out the left side of Newton's second law for 3 times for 3 different bodies. The first assignment I'm going to give you related to this is just filling out free body diagrams. You're not going to worry about the equations, but you'll see that once we're done with that, it's going to be an easy step to go from this to popping this stuff into equations. Okay. Anybody have any questions on this? Oh, I have one more thing to say. I sort of glossed over the fact that these normal forces are pushing on both pairs of wheels. You know, and that's because we're still treating this as particles. And particles we treat as having no length dimensions or anything. So I'm just concentrating that normal force into one spot. Later on, when we talk about rigid bodies, it would be important to spread it out over the 2. Okay, but for now, you can just think of it as happening at one place at the bottom. And this is where the day class is right now. So let's stop here, and then we'll get into pulling forces and friction forces on whatever day, Tuesday. Okay, bye.